the third lecture about multiplicity theory and ideals of König type. Do you hear me? I mean, can you write in the chat box if the sound is fine and you hear me? Okay, fine, thank you. So, what we saw in the second lecture was a nice theorem by Serre on the Euler characteristic of the causal homology. We saw that when we have a multiplicity system, and this Euler characteristic is either 0, or in the case that this sequence is a system of parameters for the module, this is exactly the multiplicity of M with respect to the ideal generated by this sequence. Today, our goal is to prove a nice criterion for Cohen-Macaulayness in terms of the Euler characteristic, I mean the vanishingness of some partial Euler characteristic, and using the theorem that we had in the second lecture, we can explain this criterion in terms of multiplicity. So let's start. If you remember, I introduced the modified multiplicity of a module with respect to an ideal to be 0 when dimension of M is less than Q, and just the multiplicity if dimension is exactly Q. It was left as an exercise that this EQ is additive on short exact sequences. I want to use this fact to prove a nice equality for this invariant in terms of multiplicity with respect to some quotient rings. So let's see this proposition. Before I write the statement, let me write again, repeat the condition that we have on the ring. So this lecture, R is always either a Noetherian local ring or a finitely generated standard graded K algebra. Where K is a field. And M is always a finitely generated, in the case of the graded ring, to be graded R model. So this is our setting for the whole session, unless otherwise precisely stated. We want to show that whenever we have an ideal of definition of R, which is simply an M primary ideal, which M is the maximal ideal of a ring, then we have EQ of I and M. Also, okay. Suppose that M belongs to this category that we introduced yesterday, which means that they have dimension at most Q. Then EQ of I and M can be written as in terms of the multiplicity of some quotients of the ring R, which means such rings where the sum runs over all the prime ideals with dimension Q. So we are going to prove this equality, which later we use in the proof of, later we see. So our module comes from the category of finitely generated modules with dimension at most Q. First, suppose we consider the case that this dimension is strictly less than Q. In this case, by definition, this number is 0. And it can be easily seen that the right side is also 0 because either P belongs to the does not belong to the support of M, which means that this module is 0, so the length is 0. And in the case that P belongs to the support of M, because we assume that dimension of M is strictly less than Q, then all these dimensions are strictly less than Q, such rings. So we have nothing from the support that appears in this summation. So both sides are 0, equal to this sigma, and we have nothing to prove. Therefore, we may consider the case that dimension of M is Q. I want to use this additivity of EQ on short exact sequences. So I want to produce some short exact sequences from M. For this purpose, I consider again a prime filtration of the module. Let this chain of submodules be a prime filtration. In the graded case, we may assume that this is graded. Which means that all these quotient modules Mi mod by Mi minus 1 are isomorphic to such rings where PIs are prime ideals. And of course, in the case of graded, they are also graded. Then we have these obvious short exact sequences. Mi minus 1, Mi. So here R mod Pi 0 for all I. And I apply EQ I to these sequences, then we get, if do this for use this formula repeatedly, what I get is that EQ of I and M is equal to sum of these multiplicities of R mod Pi I from 0 to N. Okay. Now I want to get from this sigma what we have here. So considering again these short exact sequences, I know that support of M, I mean inductively you can compute the support of the middle one with the union of these supports. Then this is the union of support of these modules, which is just the variety of pi, I from 1 to n. Okay, this shows that the minimal prime ideals in the support come from this p1 up to pn. And also dimension of M is just the supremum of dimension of R mod pi's. And in fact, this is, I mean, for any prime ideal in the support with the property that dimension of R mod P equal to Q, which is exactly the dimension of the module itself, we know that this P should be one of these PI's because this P is a minimal element in the support. We have P belongs to this set P1 to Pn. Then what I get is that the set of prime ideals which in the support with the property that their dimension is equal to Q is just the set of prime ideals Pi with the same dimension. As I explained here. So I can write this sigma. First of all, note that if for some pi the dimension of R mod pi is strictly less than Q, then this number is 0, so we can just ignore them and write this sigma over those pi's with the dimension of R mod pi exactly equal to Q. Then I have such that this dimension is exactly Q. And as I wrote above, this set is exactly the same as the set of primes in the support with this dimension. But I should consider also the repetition. So here maybe we have P1 is equal to P2. So here I consider EQ of this ring 2 times. Therefore, I will write here, okay, I call this number T sub P, EQ of I and R mod P such that this P comes from the support. with dimension of R mod P equal to Q. Okay, what is here TP? The number of PIs with PI equal to P. Then what remains for us to show is that this TP is exactly, if you compare the formula, is just the length of MP. Okay, let's figure out what is this number. How many of PIs are equal to this P? Okay, fix some I between 1 and n. Then by this isomorphism, if we localize at this prime ideal P, we have RP by PI RP is isomorphic to MIP MI minus 1P. And this quotient ring is non-zero precisely when this PI is included in P, and because we consider some P with this property. And thus this PI should be exactly equal to P. So we conclude that MIP is not MI minus 1P if and only if P is equal to PI. Therefore, the number of PIs which are equal to P is just the number of this index I, such that here we have a strict inclusion, but not equality. I mean, if you look at this localization as a submodule of MIP, then this is just is the number of strict inclusions. So if we again consider this prime filtration localized at P, this just exactly means that just the length of MP, because when we consider this prime filtration and we localize at P, then the number of strict inclusions here just give us the length of MP, because all these quotients are isomorphic to the field RP mod by PRP. So TP is just the length of MP. So it is enough here to replace TP by length of MP. And we can ignore this condition, because whenever P does not belong to the support, immediately this MP is 0, so this length is 0. This is why you don't see this in the formula. We just have the dimension equal to Q. Okay. Maybe better unmute. Next, we are going to relate multiplicity of the module with respect to I to the multiplicity of the ring with respect to I for modules of positive rank. Okay, so we have the condition as before on ring and module. But the extra condition that we have on the module is that the module has positive rank. So and I an ideal of definition of R. Then multiplicity of M with respect to I is equal to multiplicity of R with respect to R times the rank of the module. We will use later this formula to give this nice criterion for Cohen-Macaulayness. Okay. So I remind you what it means that a module has positive rank. Let R be the rank of our module. Okay, this means that whenever we I put QR to be just a total ring of fractions of R, which means that our multiplicatively closed set is just R minus the set of zero divisors of R. Then this equality, rank equal to R, means that the tensor product of M with QR is a free QR module of rank R. So we have R copies of this ring. This means that rank of M is equal to R. Okay? Then we know that ZR is just the union of prime ideals in the S of R. So if I choose a prime ideal in the S, the intersection with S is empty. And therefore, okay, let's write this just as S minus 1M. So S inverse M localized at S inverse P, because this is now a prime ideal in the total ring of fractions. And this is isomorphic to and this direct sum localized at this prime ideal, and we know that this is just a direct sum of RP, R copies of it. For these prime ideals, we have this condition. and this is just MP. Okay, so we could write MP as a direct sum of RP. In particular, when the prime ideal is a minimal prime ideal of our ring, which we know that it is among the associated prime ideals, then we have this isomorphism. And the prime ideals that come from the mean of R give us the dimension of the ring. I mean, the dimension of the ring is obtained by these prime ideals. So this means that here by mean of R, I mean the set of minimal prime ideals of our ring, because we know that this is contained in S. MP is isomorphic to this direct sum. So first of all, this means that all these prime ideals are in the support of M, because from this isomorphism we can see that this is non-zero, this module. And then we have dimension of M is just a dimension of R, which we call it D. And secondly, because for these prime ideals, this quotient, I mean this localized string has dimension 0, it has finite length. MP also has finite length. And this length is just the sum of the lengths of RP. So I can write it just R times length of RP for these prime ideals which come from the minimal, from mean of R. Okay? Then we have this under this assumption that our module has rank R, we have such equality. Now we come back to the formula that we want to prove. Okay. Because now our dimension is D, I can write it as ED of I and M. And I use the proposition that we proved before this proposition, that we have this nice formula for length of MP, ED of I and R mod P, such that this dimension is precisely D. Okay. The summation runs over such prime ideals. Of course, this comes from here. And because this the dimension of R mod P is exactly the dimension of R, this means that these prime ideals come just from the mean of R. So for these prime ideals, we have this equality. So I just can write it as R times length of RP ED IRP, sorry, such that this dimension is D. So just taking out R, what remains is again, using the previous proposition, I can write it as just ED of I and okay, R times this sigma, and this sigma is exactly E of I and R by using again previous proposition. So this is just rank of M times multiplicity of R with respect to I. Okay. What we are going to do next is to define the partial Euler characteristics of a module with respect to an ideal I, and find a criterion or see a criterion for Cohen-Macaulayness in terms of the first partial order characteristic. From what we have seen so far, we know that chi of x and m is non-negative, because, I mean, by this Serre's theorem, we know that either this is 0 or it's just multiplicity with respect to the ideal generated by x. Now we want to consider the partial order characteristics for any j. We define chi j of x and m to be the alternative sum of the causal homologies but not from the beginning, from a step j on. Length of these homologies, of course. I from j to n. Here n is just the length of our sequence. So let x be just x1 to xn. And thus our causal complex has length n. And if we consider this alternative sum of the lengths of the homology from a step j on, we have partial order characteristic chi j. Okay? It is known that all these partial order Euler characteristics are also non-negative. Here we just show it for chi 1, and because we want to find a criterion for Cohen-Macaulayness, and it is related to vanishingness of chi 1 for some system of parameters. So what we are going to do in the next theorem is to show that chi 1 is always non-negative. And we see that when it's, I mean, our sequence X is a system of parameters, the vanishingness just means Cohen-Macaulayness. So let R and M be as always, or as before. And X be a multiplicity system for M. Then in part 1 we want to show that chi 1 of x and m is always greater than or equal to 0, or equivalently a length of m mod by xm is greater than or equal to chi of x and m. And in part 2, we want to show that if this sequence X is a system of parameters of M. We have some equivalent statements. The first condition is just the vanishingness of chi1. The second condition is just the causal homologies are 0 for I greater than or equal to 1. And the third condition is that M is König-Macaulay. So as you see from the statement, this vanishingness is equivalent to the König-Macaulayness of our module. Part 1 is easy to prove. We want to show that I1 is always greater than or equal to 0. We do it by induction on n, the length of our multiplicity system. Suppose that n is 1 at the first step. This means that because chi1 by this formula is just alternative sum of lengths from h1 on, but when n is 1 we only have h1. So chi1 in this case is just the length of the first homology, and the length of any module is always greater than or equal to 0. Now let n be greater than 1. Then chi of x and m is just the alternative sum of all the lengths of all the homologies, and chi1 is the length from h1 on. So if I write down just the length of h0, we know that h0 of x and m is just m mod by xm. So I write just length of m mod xm here, minus the alternative sum from the first length of the first homology, which is chi1. And then I can write chi1 as length minus chi. And because I want to use the induction hypothesis, if you remember, we had a formula for chi of x and m in terms of chi of x prime, which we remove x1 and consider from x2 on. I apply this here. And so I will write it as chi of x prime and m mod out by x1m plus chi of x prime and 0 colon x1m. This was the formula, where here x prime is just the sequence x2 up to xn. Okay. I can look at this quotient module also as m mod x1m divided by x prime m mod by x1m, right? They are isomorphic. Then the length of this module minus chi of, you see here is x prime and here is also x prime. So length minus chi is just chi 1. So this is just chi 1 of x prime and mod m mod by x1m. So I will get instead of the first difference, I can write chi 1 of x prime m over x1m, and what remains is just chi of x and 0 colon x1 in m. Okay? So here I have a sequence of length n minus 1. Then I can use induction hypothesis and say that this is non-negative. Chi we know, chi is always non-negative. So chi 1 is for sure greater than or equal to 0. Okay, so we proved the first part of theorem that chi 1 is always non-negative. Let's go to the hard part, which is the second part. We want to show the equivalence of these three statements whenever x is in addition also a system of parameters for the module. Some implications are clear. For example, from C to B to A, we see that it's not a big deal. From C to B, because now in our assumption, X is a system of parameters. And whenever our module is Cohen-Macaulay, then this is a regular sequence indeed. And for regular sequences, this is known that all the causal homologies, I mean from 1 on, they are 0. So nothing to prove. And from B to A, just by the definition, chi 1 is just the alternative sum of lengths of these homologies. And whenever all of them are 0, this sum is also 0. So I just write here clear or easy to see. I don't know. The hard part, in fact, is from A to C. And the proof is relatively long, but we try to manage it. Okay, so our assumption is that chi 1 is 0. We want to use induction on dimension of our module. Okay, so we use induction on D equal to the dimension of M. Okay, in fact, this dimension is exactly n, I mean the length of our sequence. Why? Because X is a system of parameters for M, so the length is exactly the dimension. Okay, if n is equal to 0, then any zero-dimensional module is Cohen-Macaulay, clearly. So we assume that D is positive. Since we want to use induction, somehow we should produce a module with a smaller dimension and with the same situation like here. And for this purpose, I have this nice formula that we use for the first part. Here, because chi1 is 0, and this is the sum of two non-negative integers, this means that both of these numbers should be 0. So I call this formula by, I don't know, star. So by a star, we know that both these numbers are 0. And here I have this module, which we divided the module M by an element coming from a system of parameters. And the system of parameters have this nice property that when we divide, the dimension goes down exactly by the as the length of this sequence that we divide. So dimension of M mod x1m is just the n minus 1. And it can be easily seen that x prime is a system of parameters of m divided by x1m, because it has the right length, and when you mod out, we just get m mod by xm. So by induction hypothesis, we can say that this quotient module is Cohen-Macaulay. Okay, somebody wrote a question. Can you explain again how from C to B to A? Okay. There is no C, but I have in mind what was C. C was M is Cohen-Macaulay. We wanted to show that all the homologies are 0 from 1 on. The reason was that this sequence X was SOP by our assumption. And whenever we have a Cohen-Macaulay module, every SOP is a regular sequence. And this is a standard result in about causal complexes. You can see the proof, for example, in the book of, the reference that I introduced you, either Cohen-Macaulay rings by Burons and Herzog, or the book Monomial Ideals, that whenever X is a regular sequence, then these homologies are 0 for I greater than or equal to 1. Okay? And from this, we wanted to show that whenever this holds, chi1 is 0. So what was the definition of chi1? It was just length of h1 minus length of h2 plus length of h3, etc. So all the alternative sums until the last one, which is hn. Okay, when all of these are 0, then all these lengths are 0. So chi1 is 0. Okay? Any other question? Let's go back to the proof. We have this assumption that chi1 is 0. by this equality, we say that these two numbers are 0, and we use the induction hypothesis for this module with a smaller dimension, that whenever this chi1 is 0, this module is Cohen-Macaulay. Okay. If we can prove from this, I want to use this. Okay, let's go back here. I want to use this equality to show that x1 is a non-zero divisor of the module. If we are able to do this, then we are done. Why? We show that x1 is a non-zero divisor. Because then in this case, you know that depth of this module is just depth of m minus 1. And the dimension, we already know that it's dimension of m minus 1, as I told, because this comes from a system of parameters. And when these two numbers are equal, these two numbers will be equal, and we will be done. So what remains for us to show is that x1 is a non-zero divisor, which needs some effort, in fact, to do it. This is equivalent to say that equivalently the annihilator of x1 in M is 0, right? As a submodule of M, we want to show that this is 0. We consider this short exact, in fact, this diagram of we have a natural short exact sequence always from a submodule to the module. I write this down. Okay. Or maybe I call this n, maybe this is better. I call this module M1 because later I will use another quotient module of it and looks bad. So I call this M1, where M1 is just this quotient module. Okay. And I make a commutative diagram which I just consider a map from each of this module to itself, which is defined just by product, multiple everything by x1. So here I have from M to M multiplication by x1. In both rows I have the same short exact sequence. And here again multiplication by x1. Because all the maps are defined in a natural way, and these are just multiplications by the same element. Obviously, this is a commutative diagram. I will apply a snake lemma to this diagram. What I have from the kernel of the first one to this kernel, and from the co-kernels. But what is the kernel of the first one? You see this map sends everything to 0 because we choose an element in the annihilator, and when we multiplied by x1, this goes to 0. So kernel of this map is just the whole thing. Sorry, I should go and back. And here the kernel is just the annihilator of x1 in M, and here the kernel is just the annihilator of x1 in M1. And then the co-kernels. The co-kernel here is just the module itself, because the image was 0. And the co-kernel for the second and third obviously are of this form. I call this, these two homomorphisms are important for us here and here. First of all, this phi just maps everything to itself, because this is what the map here does. As a submodule of the module, sends everything to itself. So this is an isomorphism, in fact. What does this mean? This means that this map is a zero map. Because here the image is everything, so here the kernel is everything. This means that it sends everything to 0. We want to show that psi is 0. I don't go very detailed in the proof, but I explain the reason why this is 0. In fact, we want to show that, sorry, this is not psi, this is psi, okay. I want to show that or more. The only homomorphism, R module homomorphism that we have from here to here is just a 0 homomorphism. Okay. So if we show that this home is 0, this means that psi, which belongs to here, is 0. But to prove this equality, just it's enough to show that, again, I call this to be n. I leave it to you to show that dimension of, just comparing the dimensions. Dimension of n is strictly less than the dimension of m mod x1m. In fact, we saw that this is exactly n minus 1. So if you can show that this is less than or equal to n minus 2, then we have this inequality. And when we have this situation, then the annihilator of n is not included in the set of 0 divisors of the second module. This can be easily seen if you look at this 0 divisor as the union of the prime ideals which come from the S of this module. And if some prime ideal contains annihilator, this means that this P belongs to the support of n. So the dimension of n would be at least n minus 1, which is not possible by this inequality. So we have this situation, and this is a very easy exercise, in the basic courses in algebra, that when we have this condition, then this home is 0. Just choose an element in the annihilator which does not belong to these 0 divisors. If you choose an element here, then phi of Rx is 0 for all R, and this is just R phi of x. And because R is a non-zero divisor of the second module, this means that phi itself is 0. So you can write it more carefully, but this is the reason that why this home is 0. So this map is also the 0 map. Then what we get from this exact sequence is that these two modules are isomorphic, and these two modules are isomorphic because these two maps are 0. Okay. What we want to do is to replace m by m1 and continue with m1. So we should have the same condition that we have for x to m1. If you just use this formula that I showed it by a star for chi1 and use these two isomorphisms, because we know that for m this chi1 is 0, you can get chi1 is also 0. So I repeat it again. To prove that this is 0, just apply this formula, some kind of inductive formula that we had for chi1 in terms of a quotient module and some annihilator. And then replace in this formula these two isomorphisms. Then we get, in fact, this is exactly chi1 of x and m, and we knew that this is 0. So we have the same condition that we had for m for m1. Then we continue by what we did for m to m1. So from m1 I can get m2 with the same condition. So what is m2? Maybe it's not a good word to say replacing. I say repeating the procedure. Repeating. This procedure for m1, we get m2, which is m1 divided by x1 m1, such that, annihilator of x1. I mean exactly the same structure that we get from m to m1. So I just replace m by m1. And I get m2. And because we have this condition for m1, I can have these two isomorphisms for m1 and m2. m2 mod out by x1 m2. And annihilator is isomorphic for m2. So we can do it for as many steps as we like, and similarly get mk for k greater than or equal to 2. Now we consider, I call it phi k because it depends on k, to be the composition of all these, you know, from M1, M1 to M2, I have the just natural map, which maps everything to its residue class. So I will have from M1 to M2 to MK, I call this Fk minus 1. So I will have a map from M to Mk for each k. I call this map phi k, which is just this composition. Because all this map are just the natural, defined in a natural way, just map everything to its residue class. I leave it to you to show that kernel of each phi k, just by taking an element and apply it to this composition, you can easily find out that this is just this submodule. Okay. Somebody wrote M2 is M1 mod out by 0 colon x2. No, we keep the same element x1. Here, you mean M2? We keep the same element. Here it's just x1. So in general, mk is just mk minus 1 divided by 0 colon x1 in mk minus 1. Yeah. Okay. So far, we constructed some homomorphisms phi k's with these kernels. Now I consider this ascending chain of submodules of M, because our module is Noetherian. This chain stops. So I suppose that this is the step that this chain stops. I have these equalities, so on. This is the kernel of phi r. This is the kernel of phi r plus 1. So I consider from M to Mk, here I have phi k, and here I call it Fk, if you remember. And the whole thing is just phi, this should be R. And this is phi r plus 1. What we know from this equality is that kernel of phi r is just kernel of phi r plus 1. Then it is not hard to see that in this case, Fr is in fact an isomorphism. It can be easily done. First of all, phi r is an epimorphism because this is just the quotient module of Mr, and we map it naturally. So let's check the kernel. Let some element x be in the kernel of Fr. This means that Fr of x is 0. But this x comes from Mr, and we know that this phi r is surjective because it's a composition of surjective homomorphisms. So this x comes from something here. So let's say this x be phi r of some m. Then I have phi r, Fr phi r of x is 0. And this is just phi r plus 1. So phi r plus 1 of x is 0. This means that x belongs to the kernel of phi r plus 1. But this is exactly the kernel of phi r. So this means that this is 0. Phi r, sorry, this should be m. I replaced x by phi r of m. Then this is 0. But this is exactly x. So any element in the kernel is going to be 0. So fr is an isomorphism. So we are close to the end of the proof. Now we know that we use this fact that I keep this because I want to now use it. As I told you, when we continue this, we have it for up to any steps, any step k that we like. Then by this information that fr is an isomorphism, I know that the kernel is 0. But what is the kernel of fr? If you remember, this is just mr mod out by 0 colon x1 mr. So the kernel of fr is just this thing here. But from these isomorphisms, because we can go as far as we like, if we go r steps, this is 0 because we proved that phi r is injective. So this is 0. This means that, I mean, if I call it number 1 and I call this number 2, from 1 and 2, I get 0 colon x1 in m is 0. So this was the thing that we wanted to prove, to complete the proof. So x1 is a non-zero divisor. Okay, we can have a break. Okay, welcome back. Let's continue. Now that we proved this criterion for Cohen-Macaulayness in terms of the first, I mean the partial order characteristic, we are able to write down this Cohen-Macaulay criterion in terms of just the multiplicity. Okay, so let R be as before, which I mean is either a Noetherian local ring or a positively standard graded ring over a field K, and M is just a finitely generated R module, which in the case that our ring is graded, this is also graded. We suppose that M is of positive rank. Okay, and X be a system of parameters. Let's say x1 up to xd. Of M. Then we have, first of all, this inequality. Length of M divided by IM is greater than or equal to multiplicity of R with respect to I times rank of M. And M is Cohen-Macaulay if and only if here we have equality. Okay. So in particular, when I have just a ring, I mean, if M is just a ring itself, this means that length of R mod I is just multiplicity of I and R. And because in this case, a rank of R is just 1. So let's see this proof. Okay, in the previous theorem, we saw that chi1 is always greater than or equal to 0. And chi1, as we discussed, is just length of M divided by, okay, the ideal generated by X, we call it I. So this is just length of M divided by M. Is greater than or equal to chi of X and M. But because by our assumption X is a system of parameters for the module, by Serre's theorem we know that chi is just multiplicity of M with respect to I, right? And also we had a theorem that when M has positive rank, which is the case here, multiplicity of M with respect to I is just multiplicity of R with respect to I times rank of the module. So we just applied what we proved so far. Then we get this inequality. Okay? And for part 2, because from the previous theorem we know that M is König-Macaulay, if and only if chi1 of X and M is 0 for a system of parameters X. And when here the inequality becomes equality, means here we have equality. So just here, instead of inequality, I put equality. So we get this nice result for König-Macauliness in terms of length and multiplicity. And as I told you, when we have the ring itself, this means that you just check, because in this case we know that length is just multiplicity of R mod I. This ring is a 0-dimensional ring because we divide the ring by a system of parameters. So R is König-Macaulay if and only if these two multiplicities are equal. Okay. Now we want to consider a positively graded ring and see what this equality means whenever we have a positively graded K-algebra. Before I do this, I'll give you an exercise about multiplicity, which I'm going to use, in fact, for the next result. Okay, let R and M be as always. I mean, with the assumption that we have D be the dimension of our module. And then, first of all, show that if I is an ideal of definition of M, then multiplicity of I to some power L. So we consider the power of the ideal I. Multiplicity of m with respect to this power is just this L to the power d, which is the dimension of our module, times multiplicity of m with respect to I. Okay? This can be shown directly using directly the definition of multiplicity in terms of this limit, if you remember. The definition of multiplicity was in terms of a limit. If you just apply the definition, you get this equality. The second statement is that whenever we have a system of parameters, homogeneous in fact, in the case that R is graded, otherwise no matter, just be a system of parameters of M, and L1 up to LD be some positive integers. And then multiplicity of the ideal generated by F1 to the power L1 up to FD to the power LD and M is just, these powers come out. This is just L1 times LD multiplicity with respect to the ideal just generated by F1 to FD itself. Okay? So we are going to use these facts to study more this equality for, as I told you, positively graded K-algebras. Okay, so we want to find a criterion for Cohen-Macaulay property with just, explaining better this equality in terms of multiplicity, just in terms of the multiplicity of the ring itself. So our ring now is just a positively graded, a standard graded K-algebra. Where K is a field. And let F1 up to F1 up to FD be a homogeneous system of parameters of R such that degree of each Fi is, let's say, AI. Then first of all, multiplicity of, I put I to be the ideal generated by F1 up to FD. So I just can simply write I. Then multiplicity of R mod I, which we know is just the length because this is a zero-dimensional ring. And this is greater than or equal to A1 times AD, this degrees times multiplicity of R, okay, and R is Cohen-Macaulay if and only if here we have equality. So somehow we get rid of the multiplicity of the ring with respect to the ideal I. Here we just have the multiplicity of R itself, I mean with respect to the maximal ideal. Okay. Let's see the proof. Okay, by the previous theorem, we saw that we have always this inequality, multiplicity of R mod I, which is just the length, is bigger than or equal to multiplicity with respect to I. Okay? So what we should do here is just somehow compare this with the multiplicity of R with respect to the maximal ideal, which is just E of R. To do this, I consider A to be just the product of all the degrees, A1 to AN, and for each I set BI to be A divided by AI. Why I do this? Because I want to produce elements of the same degree, namely each Fi. If I consider for each I Fi to the power Bi, then the degree of this element is just AI times Bi, which is A. So all of these elements are of the same degree A. So they belong to the maximal ideal to the power A. Okay? Or in other words, the ideal generated by this sequence is contained in M to the A. Okay? This implies that multiplicity of or ring with respect to this ideal, which is just, let me write it down below, then I have more space. F1 to the A1, FD to the AD, and M is bigger than or equal to, R, bigger than or equal to multiplicity of R with respect to MA. Okay? Then using the previous exercise, I can write this as A to the dimension of our ring, which is D, the length of our SOP. And this is just E of R, so this is A to the dE of R. And again, using the second part of the exercise, I can write this as A1 times AD multiplicity of R with respect to F1 to FD. Okay? So what we have here is this inequality, And I'm going to divide both sides by A1 times AD. Then here I will get E of, and this ideal generated by F1 to FD is just the ideal I itself. So E of I and R is greater than or equal to A to the D divided by, sorry, here instead of, because I considered this should be BI. So all of these are BI for sure, because I want to produce a sequence of the same degree, sorry. The powers are just BI. So here I have B1 times BD. I can write it as A divided by B1, A divided by BD, and this is just A1, and so on. This is just AD. Something here I have. So I have just A1 times AD multiplicity of R. Okay, so we show that multiplicity of I with respect to I is greater than or equal to this number. And when we also we had this inequality, so I can apply, I mean combining these two inequality, I will get what we want, which is multiplicity of R divided by I is greater than or equal to this. We had this before, and now we get this inequality. Okay, so we have always this number bigger than or equal to this number. For the second part, we want to show that here we have equality if and only if R is Cohen-Macaulay. So if we have, first of all, suppose that we have equality. Let E of R mod I be just A1 times AD multiplicity of R. This means that both inequalities here are equalities. In particular, I have this length, which is just multiplicity, is equal to multiplicity of R with respect to I. And this is just a statement of the previous theorem. We say that if length of M mod IM is just multiplicity times rank, which rank is here 1, and then our module, which here is just the ring itself, is Cohen-Macaulay. Okay? So for this, we just use the previous theorem. So what remains is the other side. Now we suppose that R is Cohen-Macaulay. We want to show that here we have the equality. Okay. What happens when R is Cohen-Macaulay? First of all, our system of parameters is a regular sequence, which is always the case in Cohen-Macaulay rings. So F1 up to Fd is in fact a regular sequence in R. Okay. But whenever I divide a ring by a regular sequence, then I can obtain its Hilbert series. So here I is just the ideal generated by F1 to Fd. So I divide R by a regular sequence. It can be not so hard to see that this is just the Hilbert series of the ring itself times these polynomials. This A1 is just the degree of F1 and so on. You can prove this equality by induction on D, the number of this sequence that you divide. And for the first step, just use this short exact sequence because we want it to be graded. I do this shifting. This homomorphism is just multiplication by F1, and this is the ring R divided by F1, 0. Use the additivity of lengths, or let's say Hilbert function, which means that in particular the Hilbert series of the middle module is the sum of these two Hilbert series, and work on this, then you get this formula for the first step. And for the next step, just use induction and reduce by dividing over a non-zero divisor. Okay, so we have this equality for the Hilbert series, but because this, if you remember, the Hilbert series could be written as a fraction, and in the denominator we had 1 minus t to the power of the dimension, but this ring is 0 dimensional because we divided by a system of parameters. So in this case, Hilbert series is just denominator, which we use this notation for this function. And this is equal to, I write the fraction for the ring itself times these polynomials. Okay. So I can rewrite this in this form, QRT 1 minus t to the power A1, because this power is just a number of this parenthesis. 1 minus t AD, 1 minus t. And we know that this is just sum of t to the power I from 0 to A1 minus 1, and so on. Okay. So if I replace them by these polynomials, we know from the first lecture that the multiplicity of R mod I is just QRI in 1, right? So let's compute it from this equality. This is just QR1 times, here if I put t equal 1, I will get this sigma A1 and so on. So here I have A1 times AD. Okay, and what is QR1? It's just E of R. So we get the desired equality in this case. So in particular, if I consider a system of parameters of linear forms, the ring R is Cohen-Macaulay if and only if these two multiplicities are equal. I mean, all of these are 1. So we just should check that multiplicity of the ring divided by the system of parameters is just a multiplicity of the ring itself. Okay. Okay, we are done for today. Tomorrow we will discuss some applications of this criterion for Cohen-Macaulayness, and we will study them in ideals, which we call them ideals of König type. Okay, thank you very much for following. Goodbye.